Take a close look at this image. To most people, this looks like a pilot's worst nightmare. But to an engineer, this is a masterpiece. This is a triumph of design. On September 3, 2025, something incredible happened. In a single day, two different business jets, a Gulfstream G150 in Chicago and Challenger 300 in Boca Raton, overran the runway. Both planes were heavy, moving fast and running out of pavement. Both should have ended up in a highway or a building. But they didn't! They stopped safely, the passengers walked away, and the planes didn't even catch fire. They were saved by a technology that hides in plain sight at the end of the runway, EMAS, the Engineered Materials Arresting System. Today we are going to look at the hidden engineering that keeps you alive when a landing goes wrong. But first hit the like and subscribe button. This simple action is vital for me. Thank you very much. The science of soft concrete. So what actually is a mass? If you look at the end of a runway, it looks like a normal extension of the pavement. But it is not. It is a trap. The secret lies in the material itself. This is made of cellular cement, also known as format concrete. Imagine a block of concrete, but instead of being solid, it is filled with millions of tiny air bubbles, like a honeycomb. The engineering brilliance here is not about strength, it is about weakness. Normal concrete, the kind you walk on, is incredibly strong. It can withstand pressure of 4,000 psi, pounds per square inch. If a plane hits that, the landing gear snaps. But EMAS blocks are engineered to be weak. They have a specific crush strength of only 30 to 50 psi. Compare 4,000 to 30 or 50. This number is very precise. It is strong enough to support the weight of a fire truck or a maintenance vehicle without braking. But the moment the thin tires of a heavy jet hit the blocks, the material gives up. It crushes instantly. Part 2. The physics of arrestment. When a plane enters the EMAS bed, the tires slice through the material like a knife through dry foam. The wheels sink into the bed. This creates drag. The material absorbs the kinetic energy of the moving aircraft and converts it into mechanical crushing work. It acts like a giant brake pad made of stone. The system is designed to stop a critical aircraft, usually a heavy jet, entering the bed at speeds up to 70 knots, about 130 km per hour. And the most important part, it does this smoothly. The bed is usually built as a ramp. It starts shallow, maybe just a few inches deep, and gets deeper towards the end, sometimes up to 30 inches. This slows the plane down progressively, so the passengers don't feel a violent impact. Part 3. The problem when space runs out. Why do we need this expensive technology? Why not just make the runway longer? The Federal Aviation Administration, FAA, has a strict rule. Every runway must have a safety net. This is called the RSA, or Runway Safety Area. The standard RSA must extend 1,000 feet, about 300 meters, beyond the end of the runway. This is a flat, empty, grassy area where a plane can roll safely if it fails to stop. But look at the map. Many airports are built 50 or 60 years ago. Since then, cities have grown around them. Some airports end at the edge of a cliff. Others end at a busy 6-lane highway. Some, like LaGuardia or San Francisco, end directly in the ocean. And these places you cannot just add land. It is physically impossible or financially ruinous. Part 4. The economic solution. This brings us To the economics of safety, let's look at the real example. Greenville downtown airport. They had a steep drop-off at the end of their runway. To build a traditional 1,000-foot safety area, they would have to build a massive earth embankment. The estimated cost was $16 million. Instead, they installed an EMAS. Because the material stops planes so efficiently, you don't need 1,000 feet. You can do the same job in a much shorter distance. The cost of the EMAS? $1.8 million. Compare one more time, 1.8 to $16 million. It saved the airport $14 million, and it provides the exact same level of safety. Part 5. A history of safes. This is not theoretical. This technology has a proven record called Tombstone technology. Solution born from past accidents, but now saving lives. Since the first successful safe of a Saab 340 at JFK Airport in 1999, EMAS has stopped dozens of aircraft. In Charleston, West Virginia, a CRJ-200 regional jet aborted its takeoff. The runway ended at a steep mountainside. The EMAS caught it just in time. In Tattleboro, a Gulfstream 4 was stopped before it could cross a busy highway. And of course, the events of September 2025. 2 jets, 2 wet runways, 2 potential tragedies, 0 fatalities. But EMAS is only the last resort. Ideally, we never want to use it. To understand how we keep planes on the runway, we have to look deeper. We need to look at the invisible battle happening between the tire and the pavement. And it all starts with a formula from NASA. Part 6. The physics of touchdown. The most dangerous enemy of a landing aircraft is not wind, and it is not pilot error. It is water. When a plane lands, it is not just rolling. It is fighting a hydrodynamic battle. If the water on the runway is deeper than just 3 millimeters, 0.1 inches, a phenomenon called dynamic hydroplaning begins. The water builds up pressure in front of the moving tire. It forms a wedge that physically lifts the rubber off the concrete. In the 1960s, engineers at NASA's Langley Research Center, they found that the speed at which you lose control depends on only one variable. It doesn't matter how heavy the airplane is. It doesn't matter how skilled the pilot is. The only thing that matters is the tire pressure. They created a formula that is still the Bible of aviation safety. Vp equals 9 square root of P. Here, Vp is the hydroplaning speed in knots, and P is the tire pressure in psi. Let's look at the numbers. A commercial airliner like a Boeing 777 has very high tire pressure, around 200 psi. According to the formula, it will hydroplane at about 127 knots. That is fast, but it is usually below the landing speed, so the risk is manageable. Its tires are only inflated to 36 psi. The formula tells us it will lose control at just 54 knots. This means a small plane is actually more likely to hydroplane than a massive jet. Part 7. Reverted rubber, the steam seal. But there is a type of hydroplaning that is even scarier. It is called reverted rubber hydroplaning. This happens when a pilot locks the wheels on a wet runway. The friction generates insane heat. This heat boils the water trapped under the tire, turning it into a high-pressure stream. The steam gets so hot that it melts the rubber on the tire, rewetting it back to its raw, sticky, uncured state. The result is a disaster. The melted rubber forms a seal around the steam, creating a cushion. The aircraft is now literally riding on a pocket of superheated steam. Investigators know when this happens. They find telltale signs on the runway. White marks that look like the pavement has been stream cleaned, along patches of melted rubber. Part 8. Engineering the surface. Grooving. So how do engineers fight this? We cannot stop it from raining, so we change the ground itself. If you look closely at the major runway, you will see it is not smooth. This is called grooving. Engineers cut thousands of channels across the runway. The FAA has a very strict standard for this geometry. The grooves are 1/4 inch 6 mm deep. They are 1/4 inch 6 mm wide. And they are spaced exactly 1.5 inches 38 mm apart. These tiny channels give the water an escape route. It flows into the grooves and drains away, allowing the tire to grip the lens, the high points between the cuts. This simple geometric pattern can increase friction on wet pavement by up to 300%. But maintaining this is a nightmare. Every time a heavy jet lands, the tires spin up from 0 to 140 knots in an instant. This abrasion rubs off about 1.5 to 2 pounds of rubber onto the runway. Over time, this rubber fills the grooves. If 40% of the grooves are blocked, the runway becomes dangerous. That is when maintenance crews come in with ultra-high pressure water blasters, shooting water at 40,000 psi to strip the rubber off without destroying the concrete. Part 9. The layer cake. Hidden structure. Now let's go deeper. Literally. Passengers think a runway is just a road, but a highway is designed for trucks. A runway has to survive a 300-ton machine slamming into it at 250 km/h. If you sliced a runway in half, you would see it is a massive engineering layer cake, more than 2.5 meters thick. Look at the cross-section. At the very top you have the surface course. This is the asphalt or concrete we see. Below that is the base course, often made of cement-treated aggregate. Then the subbase, and finally the subgrade, the native soil. In major international airports, the top layer alone can be 22 inches 56 centimeters of solid Portland cement concrete. This is thicker than the walls of a military bunker. This structure is designed to distribute the massive points of load of a single wheel. If the layers were not there, the landing gear would punch through the pavement and sink into the dirt. Part 10. The evolution of design. For decades, engineers designed these layers using old charts and tables called the ACN-PCN system. It was based on empirical data from the 1950s. But modern aircraft gear is too complex for simple charts. In July 2020, the aviation world switched to a new standard, ACR-PCR. This is a mechanic approach. Engineers now use computer simulations called layered elastic analysis. They model the runway as a multi-layered elastic system in a digital environment. They can predict exactly how the pavement will bend and rebound under every single wheel of an Airbus A380. Part 11. The chemistry of asphalt. Finally, even the asphalt itself is high-tech chemistry. It is not just tar and rocks. Engineers use a performance grading (PG) system to design the binder. In a hot climate like Dubai, they might use PG 7622. The 76 means the asphalt won't melt or rot until it reaches 76 degrees Celsius. To achieve this, they modify the bitumen with polymers like CBS. It is basically turns the road into a very stiff rubber band. In a cold climate like Alaska, they use PG 5234. The 34 means it stays flexible down to minus 34 degrees Celsius, so it won't crack in the winter. We built the ground to match the sky, but even the best pavement is useless if the pilot can't see where to land. That is where the engineering of light comes in. Part 12. Tombstone technology. There is a dark saying in aviation: regulations are written in blood. Engineers call this tombstone technology. It means that many of the safety features we see today were invented only after specific disaster. Take the tragedy of American Airlines Flight 1420. In 1999, an MD-82 jet overran the runway in Little Rock, Arkansas. It didn't stop in the grass. It collided with a rigid steel walkway that supported the approach lights. The steel structure didn't break. Instead, it tore the aircraft apart. That accident forced a critical change in engineering. It is called Frangibility. Today, strict FAA rules state that any object located in the runway safety area, whether it is a light pole, a sign, or a navigation antenna, must be frangible. This means it is engineered to be brittle. It is strong enough to stand up to a storm, but designed to snap, buckle, or yield instantly if an aircraft hits it. The object must die, so the passengers can leave. We see this pattern everywhere. After the collision of two Boeing 747s in Tenerife in 1977, airports were required to install ground radar (ASDE) to see through fog. After the crash of Singapore Airlines Flight 006 in 2000, where a pilot turned onto a closed runway by mistake, lighting standards changed. Now taxiway lights must be physically locked out so they never lead a pilot to a closed runway. Part 13. The language of light. But the best safety system is one that prevents the accident before it happens. This brings us to engineering of light. When a pilot approaches a runway, they don't just guess their altitude. They look for a box of 4 lights on the left side of the runway, the precision approach patch indicator. It looks simple, but the optics are incredibly precise. The system is calibrated to define a perfect 3-degree glide path. Each light unit projects a split beam. The top half is white and the bottom half is red. The transition between the two colors is razor sharp, less than 3 minutes of arc. This creates a simple code for the pilot. 4 white lights, you are too high, more than 3.5 degrees. 4 red lights, you are too low, less than 2.5 degrees. This is dangerous, you might hit terrain. 2 red and 2 white, you are perfectly on the 3-degree path. Part 14. The runway is talking. Once the wheel touches the ground, the engineering shifts from guidance to distance. At night, a pilot cannot easily see how much pavement is left, so the runway talks to them using color codes mandated by the FAA. The centerline lights, the lights running down the middle of the runway, are not just white. When there are 3,000 feet remaining, the lights start alternating red and white. This is the first warning. In the final 1,000 feet, the center line turns solid red. This tells the pilot, you are running out of space. Stop now. Even the edge of lights participate. In the last 2,000 feet, or half the runway length, the white edge lights turn yellow. This creates a visual caution zone for the pilots. Now I'm serious. Which part of this hidden engineering surprised you the most? Was it the soft concrete of EMAS, or the fact that NASA formulas control your landing? Write your thoughts below, I read every comment. If you learned something new today, hitting the like and subscribe button is the best way to support me. As a new channel, every subscriber truly counts and motivates me to create better stories. Click here to watch the next video. Thanks for watching and see you in the sky!